Okay, so now let's do the correct choice. So what do we get? We get two equations, x second over x is equal to lambda, which is positive. And on the other side, we get y second over y equals to negative lambda, which is, well, negative lambda is negative and lambda positive. Okay, so that means that my x is going to be written as my sine h, cosine h composition. So we get a times cosine h of square root of lambda x plus b times sine h of square root of lambda x. And on the other hand, we get the y second over y is equal to negative lambda. So that means that y of y is going to be the c cos of square root of lambda y plus d sine square root of lambda y. Okay, so let's see what we obtain. Let me just redraw my initial conditions. My initial conditions are all 0, 0, 0 here, and I've got 1 on this side. Okay, so idea is that could you foresee that this should be the right choice? You understand that we're going to do as usual. We're going to find that lambda depends, can be something like n pi, square root of lambda should be n pi, and so that we get something that we will be able to express as a sum of cosines and sines, and that will allow us to adapt some parts, okay? So we will be able to adapt our y to this non-zero value. Okay, and whereas for which I wouldn't be able to do with just combinations of cosine h and sine h, because these are just exponentials, okay, and I can't create anything with a sum of exponential functions, whereas I can create all the continuous or continuous almost everywhere functions with the Fourier series, which are sums of cosine h, of simple cosines and sines. Okay, so whenever your boundary condition or initial conditions concerns one of the variable, this is the one that should be expressed with cosines and sines. So that should lead you to choose the right value for the lambda. Okay, so let's see what we obtain for those values. If, I don't know, let's pick them one by one. So I've got u of 0y is equal to 0. Okay, so that's this boundary here. U of 0y is equal to 0. So that means that for x is equal to 0, I get that a cos h of 0 is just 1. A times y of y is equal to 0 for all y. So that implies that a is equal to 0. Okay, so I get rid of this part, right? And then I get, what else do I have? I get, well, the two others. So u of x0 is equal to 0. So u of x0, that is, so b sine h of square root of lambda times x times c cosine square root of lambda times, well, that's just 0. Okay, so that's 1. So times c is equal to 0. Okay, so what does that imply? So if I choose that b is equal to 0, I would have that the x part is always 0, so then that, again, I will have 0 everywhere. So I must not choose b is equal to 0. The only choice is that c is equal to 0. Okay, so let's write what we have for the moment. We have that u of xy is going to be b sine h square root of lambda x d. So let's write that b times d is equal to b prime times the sinus of square root of lambda times y. Okay, one more initial condition. So what do I have? I have that when y is equal to 1, Look at the top one, okay? That one here, the top one here. I get that u of x1 should also be equal to 0. So what do we obtain for this one? U of x1 is just going to be, so I've got my b prime sine h square root of lambda times x times sinus of square root of lambda times 1 should be equal to 0. So again, I can't choose b prime equal to 0, otherwise my solution would be equal to 0 everywhere, which I don't want because I want to be able to adapt to the one on the right boundary. So it leads me to square root of lambda is equal to n times pi. Okay, and I've got my solutions. Un for any n, I can write that b prime n, which is given by, well, which we will find later on. So n pi x sinus of n pi y is my solution. Okay, and by linearity, you know that I can sum on all these solutions, and I'm going to write that sum for n, well, in n star. Well, in n doesn't change anything because for n is equal to 0, it's just equal to 0. That's just going to be equal to u of xy. So actually here I've just got one constant to find. And how are we going to find this one? But by using the last boundary condition. So last boundary condition. So we get that u of 1y, so this is the non-zero one, is a constant equal to 1. And so that means that I should have, so for x is equal to 1, my sum of p prime n sine h of n pi times 1 times the sine n pi y equals to 1. And this is where we're doing the same stuff as usual. We are going to reinterpret this as the Fourier series for function 1. Okay, but which one? Extended by, so I've got a sine Fourier series, so it means that it has been extended by odd parity and periodized. Okay, so what are we looking at? We're looking at the Fourier series of this function, so the one that is equal to 1 between 0 and 1, okay, and that has been extended by odd parity, so it should be -1 between 0 and -1, and then it's been periodized, okay, so that's it, right? So this is the function that I want to make the Fourier series of. So that means that I know that these coefficients here, okay, I know that b prime n sine h n times pi, they are going to be given by the Fourier series formula. And so if let's note this function phi of x, so if we apply the formula, that should be 1 over half a period, so my period is 2. And so 1 over half a period, that's just 1 over 1, integral between -1 and 1 of phi of x sinus n pi x dx. You should get the habit now of getting a bit faster on that side, saying that these are two odd functions. So their product is going to be one even function, so that I can write this as 2 times the integral between 0 and 1 of phi of x, which is 1 times sinus n pi x dx. Okay, which makes things much simpler because because I don't have to say, well, on -1 0 I get -1 for my function, and on 0 1 I get 1. So it's we really only have to keep one value, and so we can integrate that. This is going to be 1 minus 1 over n pi cosine n pi x between 0 and 1, so that's 2 times, that's -1 to the n, 2 times -1 to the n, minus 1, okay, divided by n pi, and that's just going to be well, I had a minus, sorry, from the minus that I've got here, right? So that's just going to be, you know, it's going to be equal to 0 every even index. And if not, if it's not even, it's going to be equal to negative 2 times negative 2 times negative 2, so that's 4 times plus 4 over n pi if n is odd. Okay, so maybe we could try this. So my solution here, the u1, I'm going to call that u1. Maybe it was intended in the well, no, because well, it's okay. It's because it's just going to be one part of my complete solution. So u1 of xt is just going to be the sum for n greater or equal to 1, n odd. Okay, so of 4 over n pi of so my coefficients. So my b coefficients, my b prime coefficients are actually what we have found, divided by sine h over n pi times so my sine h n pi x sinus n pi y. Okay, and that's it. And if you really want to express the fact that we have odd, we can write that n is 2p plus 1 for all p in n. Okay, so that's the sum for p in n, 1 over 2p plus 1 pi sine h of 2p plus 1 times pi sine h of 2p plus 1 times pi x times the sine h, oh, so sorry, the simple sinus of 2p plus 1 times pi times y. Okay, and this is our first solution.